Good morning, this is Dr. Jingbo Ruiz Liu, the organic chemistry instructor from Texas A&M University, Kingsville. So today we are going to conclude chapter 2 about alkane and cycloalkane. In this lecture, we are going to focusing on the physical properties of alkane and cycloalkane. The first physical property is about the boiling point. Boiling point of the N-alkane normally going to be increased with the increasing of atomic of a molecular mass, meaning the larger the molecule you have, the higher the boiling point will be, and correspondingly the higher the melting point will be. If for the same molecule, for the same formula, the branched alkane, generally speaking, has a lower boiling point or melting point compared with the unbranched alkane. The reason we are going to learn is because of the intermolecular forces. Before, in your general chemistry, I believe you learned 6 different types of intermolecular forces which are affecting on the physical properties, especially the boiling and melting point for liquid, for solid, particularly for liquid and gas. The intermolecular forces are also known as van der Waals forces. These intermolecular forces are normally found between different molecules. In terms of organic chemistry, we can see 3 major different types. The first one called the dipole intermolecular forces, including hydrogen bonds. The second one called the dipole-induced dipole. The other one is called London dispersion. Also, you can consider it for the nonpolar molecules. Between nonpolar molecules, you are going to find the dipole-induced intermolecular forces. For your alkane, most of them are nonpolar molecules. They don't have dipoles. Therefore, the van der Waals are temporary. So it's instantaneously occurring. Normally, this kind of van der Waals intermolecular forces known as London dispersion, or you can say dipole-induced intermolecular forces. They are weak. They are going to be short-lived. The interaction, again, is dynamic, and this interaction fluctuates due to the instantaneous occurrence of your dipole moments. Intermolecular forces and your alkane normally can be described by the London dispersion formation. If you have branched alkane, the branched alkane normally have lower surface areas compared with the isomeric N-alkane without substituents. Therefore, the branched alkane normally have lower boiling points. Correspondingly, the melting point will be also lower. For example, I have pentane, I have mesylpentane, I have dimesylpentane. You can see the melting point, the boiling point for these 3 different formulas or 3 different isomers are from 36 Celsius, decreases to 28 Celsius, and further decreases to 9 Celsius. That's what you are going to see for the melting boiling point, differentiated based on the isomers. If you have the same formula for the different isomers, they are going to have different physical properties in terms of a melting and boiling point. If they have a different number of N, the larger the molar mass is, the higher the melting and boiling point. They're very similar to each other. Boiling and melting point essentially have the same trend. Also about the density, if you have the unbranched, non-substituted alkane, they have higher symmetrical system. The symmetry is higher, therefore the density will be also higher. Due to the slightly stronger London dispersion, intermolecular forces hold the molecule together in a little solid approach. And about the solubility of the alkane, we know most of the hydrocarbons, they are not soluble in water. They are hydrophobic. So virtually you're not going to see them soluble. If you put them together, the alkane is normally going to be floating on top of the surface for your water. The density of most of the alkanes are in the range of 0.6 to 0.8 grams per milliliters. Other physical properties can be related to the colors, and also the acidity of hydrocarbons sometimes can be detected. So you have your hydrogens. These hydrogens can be donated as a proton. Therefore, your hydrocarbon can display a very weak brownish lauric acid. You are going to use the pKa or Ka to denote it. Normally, if you have a higher pKa, the stronger the acidity will be. The higher the Ka, the stronger the acidity. Be a little bit careful. pKa represents to the negative log of Ka. And the hydrocarbons, normally they are going to be reacted. The reaction is commonly known as a combustion reaction. This combustion reaction of hydrocarbon refers to the hydrocarbon reacted with your oxygen to produce a final product, carbon dioxide and water steam, water vapor. Most of the cases, this hydrocarbon combustion reaction is the exothermic reaction. The delta H actually is very large, can be negative 3,529 kilojoules. So this is in terms of the hydrocarbon combustion reaction. Also, you can use the heat of combustion to determine the stability of your different hydrocarbons. What we are going to see, if you have the larger hydrocarbons, the very larger hydrocarbons normally related to the less stable isomer. The lower the heat of a combustion is, the more stable that related isomer will be. And then hydrocarbons, they usually can subject to the oxidation reduction reaction. In terms of your carbons, I listed the oxidation number of the carbon in the different compounds. If you have your carbon in the methane, CH4, this carbon in methane has an oxidation number -4. If you have your methanol, oxygen in this methanol has an oxidation number -2. If you have a carbon monoxide, carbon can have an oxidation number +2. If you have your carbon in your formic acid, in the acid, carbon also have oxidation number +2. Carbon by itself has an oxidation number 0. Carbon in the formaldehyde can have oxidation number 0 as well. Carbon in most of the carbonic acid and other acid, in most of the acids, can be +4. Carbon dioxide for carbon also has +4. Again, your carbon +4, -4, -2, 0, +2, +4, etc., etc. Oxidation reduction reaction occurs in the hydrocarbons. Normally, oxidation of your carbon corresponding to the oxidation number of carbon atom. Reduction reaction related to the oxidation number of carbon decreases. So that's the oxidation and reduction reaction. Oxidation meaning losing electron. Reduction reaction meaning gaining electron. So in the future, when we're moving on further to the different chemical reactions, we are going to learn a little bit more. There's some other element if they bonded with carbon, such as you have a positively charged metal. So you have a methyl lithium. So the oxidation number of carbon is also -4. So this compound can be used as a very reactive catalyst for future study. So isomers in the higher end alkane can be very complicated. For the higher end alkane, you can have many isomers, and it's not possible or easy for us to predict how many isomers could be formed. For example, you have carbon 1 to 3, so methane, ethane, propane, you only have one possibilities for the different connectivities. You only have one connectivity, so in this case you only have one isomer. For carbon 4, you have two possibilities, 5 carbon, 3 possibilities, 6 raised to 5. If you go to carbon 7, you can see 9. Carbon 8, you can even write it down 8 different isomers with the number of carbon increased to 40. So you see there are so many different isomers, meaning the complication will be increasing. So these hydrocarbons, they are generally speaking are resulted from the fossil fuel. So you have 3 types of fossil fuel. First one is called natural gas. Second one called petroleum. Third one you can call it coal. Petroleum can be refined. So the petroleum, so you have something called cracking and reforming. Cracking refers to the cleavage of carbon bond in the higher molar mass of alkane. So when you apply the catalyst, when you apply the heat, cracking, meaning the cleavage of carbon bond, can occur. Reforming refers to the conversion of hydrocarbon in petroleum to the aromatic hydrocarbons and also highly branched alkane. So this petroleum is meaning most of the case for me, I consider petroleum is your the gasoline which we fill into our tank for driving. There's some other naturally occurring alkane. I'll leave these different types of alkane for everybody to study for your further and comprehensive learning. So that's all for today. At this time, we conclude chapter 2, alkane and cycloalkane.